I didn't know. I have been here like just 5 or 6 minutes ago. I think it overheated. No idea. And I have an assignment due tonight.
You want some help?
Yes, I do. But who are you guys?
Well, my name is Hector Tamayo. I'm a mechanical engineer student here at FIU, and I like to tinker with cars.
And I'm Brandon Rodriguez. I'm a mechanical engineering student here at FIU, and I like to tinker with cars as well.
Oh, that's cool. I'm Arya.
Arya, good to meet you.
I'm a mechanical engineering student at FIU too.
I think I might have you in a class.
Oh, for the simulation software?
Sounds about right, yeah.
Yeah, that's cool.
So, you know how these things work?
Sorry, I had no idea about this stuff.
Well, it's pretty cool. I can actually show you something. All right, so here we have a SolidWorks simulation of a single-cylinder, four-cycle or four-stroke engine. So the reason that it's called a four-stroke engine is because as it's operating, the engine has to go through 4 strokes to complete a full cycle. Piston comes from the spark or the combustion cycle. So as we compress gases, we have a spark that ignites inside of the combustion chamber, causing an explosion that pushes the piston down with a force. And as it completes that part of the cycle, you have the completion of the combustion stroke. As it's coming back up, now you're pushing those combusted gases back out as part of the exhaust stroke. And as you continue to rotate around, now you're pulling fresh air and gas mix in, and that's the intake stroke. As the weights continue to spin you around, now you're compressing in the compression stroke up until you get to the point where you have a combustion cycle again, and you just continue the cycle repeatedly. And that's how an engine works.
Oh, perfect. So can you guys explain me how it works on each part?
Sure, so this is the piston head we were talking about before. If we go ahead and open the stress study, we can see how there's all this deformation here, but it's all green and blue, meaning it's slight deformation to little deformation. But if we notice up here, this von Mises stress is 4.3 to the 10 to the 7th, which is less than our yield strength, meaning none of this deformation will occur in an actual environment. Now, if we go over to our factor of safety for the piston head, you'll see that we have a factor safety minimum of 2.2, meaning we're 2.2 times the required limit for this part. Therefore, in a normal situation, you would not have any deformation in your piston. If we swap over to the pin, which goes inside of the piston, we can go ahead and open up this bending static study to see that we have some bending here, again, green and blue, in an acceptable range, but still, we do not surpass our yield strength, so we have none of this actually occurring within your engine in a normal situation. If we go over to our factor of safety for this part as well, we can see that we still have a factor of safety minimum of 1.8. Therefore, we're 1.8 times the required standard. So again, you will not have any bending in this part in normal situations. Now, if we go to our connecting rod as well, and we open up our static study, you would go ahead and see, we open up stress, that we do have some bending here, again, still within acceptable limits because we are not surpassing our yield strength. Our stress does not surpass our yield strength, so we're still fine. And our factor of safety for this part, it's still 1.8. It's 1.8 times the required limit. Now, when we go into our next study, which is our bending study, so this is what happens when our piston starts to go down and the rod begins to turn. We notice that we do have some red here, right? So this is where we'll begin researching optimization in terms of material and how we're gonna make sure that we can negate this as much as possible. And then we also can go into our factor of safety here, and we notice that we're at a factor of safety at 0.29, meaning we're way below the minimum threshold we have to make sure this part is optimized. So to do this, we're going to go and we're going to find the most appropriate material we can use for this part. That way we can neglect any opportunity for this part to bend.
Oh, perfect. So that's called the optimization study, where you are going to like change the materials or the dimensions, right?
Right.
Perfect. Hey, so now you had talked about the optimization study. I wonder, is that the only way that the connecting rod can fail? Is there any other way it can possibly fail?
Well, there is potential for other failure points, right? So depending on the way that the forces are acting upon the connecting rod, there's always a chance for something else to happen. But if we run a buckling study, like the one that we see here, we can see that there is potential for movement in 2 directions. However, depending on the material that you run with, this one, for example, being an alloy steel, we have a deformation scale of over 15, which means we don't actually have a buckle. And if we come and list our buckling safety factor, we're at 3.5. In an extreme case, or what we would see internally would be these forces. Again, we have a max stress that does not exceed our yield, so we don't actually have this happening within the engine. We do have, however, a torsion force as the crankshaft rotates with the forces being applied on the bearing this way. And again, we do have a max stress that is lower than the yield, so everything would be nice and safe. And if we look at the factor of safety for this part at this point, we would be at 4.2, so there'd be nothing to worry about there.
Oh, okay. So now I'm wondering, you're showing me all these parts, but can you like give me a visual representation how it would look when it's like heating, right?
Right, so if we open up a thermal study of, say, the piston, which is arguably one of the hottest parts that is inside the engine, because you have the combustion happening on the face of the piston, this is taking into account the heat power on the face of the piston, convection of the piston as a whole body, with emissivity of the heat radiation. This is a study done over a period of 10 seconds at intervals of half seconds. You can see that the heat is quickly dissipated because of the metals chosen for this piece. So under normal operation, you wouldn't have likelihood of failure due to heat. However, if your engine did overheat, that's when we come into issues where we're operating in much higher temperatures than the component is designed for, and there is potential for other components to fail, such as a head gasket or even warping the engine head itself.
Wow, that's
So in this case, where the connecting rod does have a bending moment where it connects to the crankshaft and it is displaced at its maximum angle when the force is applied, we can run a design study to try to optimize the component. By running a design study, we can compare multiple materials that we can make this component out of. As you can see here, the alloy that we originally had a minimum factor safety of 0.75 made out of the alloy steel. However, after multiple scenarios with different materials, different types of metals, the design study concludes that the optimal performance is given by this titanium alloy here, bringing our minimum factor of safety up to a 1.3.
wow. Thank you for teaching me all that, guys. Bye bye.